Hello, we got lecture 63, confidence intervals for a proportion, population proportion. And I say here, by now you should realize that all you need to know to get the confidence interval are how to calculate the point estimate and the margin of error. So what are those? The point estimate. Point estimate is p hat, which you've seen before, and that is equal to, I say here, I write here, I want you to write x over n. And you should remember what those are. If you don't, let me just refresh your memory a little bit. The idea is that I pick a sample of something. So, what am I doing? I'm looking at a population. I want to decide estimate what proportion of that population is in some category versus not being in that category, right? What fraction? Is it 20%? Is it 73%? Right? That's what I'm after here now. And so what I do is I pick a sample of size n, and I count up the ones in my sample that are in the category I'm interested in. Right? And the language we used for this was, we called n, it's our sample size, but with the language we used in this case, we called it the number of trials. But the number of times we reached into our set randomly and pulled out a member of it. And that was called the number of trials. And the x was called the number, that was the number of times we got what we were interested in, and we called that, if we got one that we were interested in, we called it a success. So this is the number of successes. Okay, so the number of successes over the number of trials. And remember, I'll say a little bit more about this later, but remember that the trials have to be independent from each other, and they have to have the same probability each time you do execute a trial. And that really amounts to saying we're picking a simple random sample from our big population. Okay, that is the point estimate. What's the margin of error? Margin of error is z alpha over 2 times p hat times q hat over n, all inside the square root. And if you remember right, you'll remember that q hat is 1 minus p hat, okay? And we had a very similar calculation when we were doing hypothesis testing. Note that we are back to using z-scores, okay? And that's what happened when we were doing hypothesis testing for population parameter, or population proportion as well. We were using z-scores instead of t-scores. We're doing that for the confidence intervals as well. That's the appropriate random variable to use, because p hat behaves like a normal random variable, not like what would be a transform t random variable. So that's kind of nice. We're back to the z-scores. Okay, and I say here, you might want to refresh your memory about all of this, and you can go back to lectures 53 to 54 for a review, or you can just kind of see if it all comes back as we work what we're going to work through here. But you should have very good notes that you've taken, right, from lectures 53 and 54, I say here. Yes. So you don't need to go back to those videos. No, just go back to your notes that you have. And that's why I want you to have those notes, so you will have those to refer to for the rest of your career if you ever need them. Let's do an example. You have a big bag of Mountain Men Trail Mix. Mountain Men Trail Mix consists of a mixture of M&M's, peanuts, raisins, cashews, and almonds. You would like to estimate the fraction of pieces in your bag that are M&M's. Now, we could figure out exactly what that fraction is, right? If we're thinking of our bag now as the entire population. It's a giganto bag. You could take all day and count all the pieces in the bag and count all the ones that are M&M's and do a fraction, and you'd have the exact answer. But we don't want to do that, where that's working with the whole population, which could be thousands and thousands of pieces if it's a great big bag. That's why I say here it's a jumbo bag. So instead, we're just going to take a sample and try to estimate the proportion that are M&M's. So what do I say here? You want to estimate the proportion that are M&M's. You shake the bag to make sure it is all well mixed. You draw one piece out. You shake the bag, draw another piece out. You keep doing this until you draw out a simple random sample of 88 pieces. You count that 16 of these 88 are M&M's. What I want is find a 90% confidence interval for the proportion of pieces in your bag that are M&Ms. What are we going to do? We're going to find the point estimate, and it's going to be that plus or minus the margin of error. That's all there is to it. So let me run through the steps here. Step 0 is kind of where we kind of check to make sure what we're doing makes sense. And I say here that it's a simple random sample. So that's really saying that the trials are independent and the probability is the same each time, right? That's what you need. And I'm going to put a little question mark here because there is a bit of an issue there that we're going to come back and explore later. But right now we're going to say, yeah, we have what we need. It's a simple random sample. And the other thing, if you remember, before we could let the central limit theorem do its magic when we were dealing with hypothesis testing, we had to have that, for the sample size to be big enough, in this case, we didn't necessarily need n to be bigger than or equal to 30. We needed the number of successes and the number of failures to be bigger than 5, right? Bigger than or equal to 5. Number of successes, we got 16 M&Ms. That's 16. That's bigger than or equal to 5. What about the number of failures? The number of non-M&Ms, well, there were 88 total minus 16, and that's 62, or no, that's 72, sorry, 72, which is also bigger than or equal to 5. So central limit theorem conclusions hold, so we can go for it, right? Central limit theorem says go for it. We should be able to make the normal approximation, which essentially means build everything out using our z random variable here. So step 1 then is point estimate. Point estimate is number of successes divided by the number of trials. We had 16 M&Ms in 88 pieces, and that works out to be 0.18, repeating 18, 18, 18, 18. And I guess I make a point here that, let's see, yeah, I say that, I guess I don't actually say it here, but our data, our counts are all whole numbers, right? So we might want to only go out to the nearest tenth. We kind of tend to go out 1 decimal point more than our data are in, and the data would be counts. But I'm going to go out 2 decimal points here because I want to stay fairly accurate. 0.18 is then what I'm going to round to. So there is our point estimate. Number 2, can I fit that in here? I think so. 90% confidence, confidence means that 1 minus alpha is 0.9, right? That's 90%. So alpha is 0.1, so alpha over 2 is 0.05. So z, is that what I'm ready for? I guess number 2 was, yeah, finding z alpha over 2. That's z 0.05, and that's 1.645. You can look that up in any table, and perhaps you have it memorized. You've had to look it up a number of times. Let's see. 3, the margin of error then is right here. Z alpha over 2, square root of p hat, q hat over n. So that is, sorry, we know what z alpha over 2 is. Z alpha over 2 is 1.645. And I want then the square root of p hat is, let me leave it as 16 over 88 right now. When I'm doing computations, I do not want to use rounded values. Remember that? We don't use rounded values in the middle of computations. So I'll leave it as 16 over 88. What's q hat going to be? Q hat, we can do it right here. Q hat is 1 minus 16 over 88, and that will be 88 over 88 minus 16 over 88 is 72 over 88. It's the number of failures divided by the total number of trials. Sorry, 88. Divide by, and then what do? We divide by n. We divide by n. So again, they're 88. All right, if you do all that carefully in your calculator, you should get .0676, 0.0676, da, 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 da. And again, I would round that then to 0.07, rounding to the nearest hundredth. Okay, so there's your answer. So 90% confidence interval is 0.18 plus or minus 0.07. Or we can write that as, when I subtract 0.07 from 0.18, I get 0.11. And when I add it, I get 0.25. Okay, so what are we saying then? We are saying our final conclusion is we are 90% confident that the proportion of pieces of Mountain Man trail mix in this bag that are M, and that's not how you make an ampersand. How do you make an ampersand like that, right? M and M's. We are 90% confident that the proportion of pieces in this bag of M and M that are in this bag that are M and M's is between, let's say, 11% and 25%. Okay, that's that. Okay, let's see. I want to say a little bit. Remember, if I am, how should I say this? If you want to give back a 90% confidence interval, let's say, which is what we're doing here, you be sure to give an interval which contains at least 90% of the confidence. So in other words, it's a good idea to round your margin of error up. If I round the margin of error up, then I start at my point estimate and I go down and up that amount. The actual amount I need to go down and up maybe is a little less, but I round it up. So it means I got a little bit more, and so my confidence levels may be actually a little higher than 90%. Now the P hat was off a little too because we rounded, but I mean, if we round up, that's a way to make sure we get 90%. If we're actually a tiny bit higher, we're at least not fibbing. What I don't want to do is round down and really only have 87% confidence when I claim to have 90% confidence. So it's a good idea to round your margin of error up. All right, yeah. I read the top of the next page there. There is something that I wish to point out. On this problem especially. I think it occurs pretty much any time you're sampling from a finite population to produce independent trials, which you're calling independent trials. But it's a little bit more poignant here maybe because I'm looking at this bag, which is quite finite. The number of pieces is not all that huge. What I say here, a few notes about the previous example. Each piece we pick out of our handful and observe whether or not is an M&M is one trial, to use the language we developed earlier. The trials are supposed to be independent, but are they? Typically, what you do is you reach in and pull one out, and then you shake it up, reach in and pull one out. Every time, if I don't put that one back in, and I could have just put it back in and shaken up again, but if I don't put it back in, and often you don't, you might just shake it up and grab a whole bunch, and that's all your trials. So they're not being put back in every time I choose the next one. Therefore, I change the relative proportions of what's in there a little bit, right? I change them a little bit. So is it really true that after maybe I pulled out an M&M, the first trial, the next trial, the fraction of M&Ms is a little bit smaller, so the probability, the proportion that are M&Ms is actually a little bit smaller. It's not quite the same as it was when I pulled the first one out. So it's fibbing a little bit to say this, that the trials are independent. And so let me make that up. And what I say here is, in that space then, each choice changes the proportion a little bit. Changes the proportions, it changes the proportions of everything a little bit. But if the bag is big, let's just say has many pieces, trying not to squeak, it's impossible. If the bag has many pieces, perhaps or probably removing only 88 doesn't change things enough to matter. All right, so in other words, if I have thousands and thousands of pieces in the bag, grabbing 88 at random is probably not going to change the proportions enough so that I have to say, oh golly gee, the probability changes each time, so I can't really do this. The theory is based on that it doesn't change, but it probably doesn't change enough that it matters. I can probably go ahead and do that. All right, so, and really I could have, after each time I pulled one out, I could have shaken the bag, thrown it back in and shaken the bag back up. So I wouldn't have changed things at all. But typically you might just, if you shake things up well enough, you might just grab all of them at once. And then you're definitely not replacing when you pick the next one. So that's something to be aware of here. But I don't think it is much of an issue. All right, one more example. So go ahead and read the example while I rub this out. We'll run through it quickly. Okay, it says, remember Senator, I am corrupt. After hiring a PR firm to whitewash his image, he has decided to run for president. Okay. In order to find out his support base, he contracts with your polling firm. You send out a questionnaire to a random set of voters, asking whether they plan to vote for him in the upcoming presidential election. Receive back responses from 560 voters, and 140 of them say they plan to vote for corrupt. Find a 95% confidence interval for the percentage of voters who say they will vote for corrupt. All right. Step 0. The trials are independent. The trials are, I poll one voter, and then I go poll another voter, and I poll another voter. I don't pull one voter and then poll his sister. I don't connect them in any way, right? I don't ask who's your best friend. I'm going to go poll them. I'm picking them utterly randomly, so they are independent. Now, it's true that they don't all respond, maybe, and so there's some self-selection there, so they might have some trait in common, so you can kind of argue that maybe they aren't independent, and polling firms have to deal with issues like that. For what we're doing here, we'll assume that they're close to being independent. We're interested in, what we consider a success, is if someone says, yes, I'm going to vote for corrupt. So N is 560, number of successes, which is X. It's 104, and that's greater than or equal to 5. Number of failures equals 560 minus 104, so that's what, 456, I think, and that is greater than or equal to 5. So, go. Go for it, proceed. Let me try a different color. Try maybe a less squeaky one. Step 1, let's do this quickly. P hat. P hat is 104 over 560. And that works out to be 0.1857, So again, I'm going to make that 0.19. Q hat is 456 over 560. And it is whatever it turns out to be. equals whatever. We don't actually need it in our final answer, it comes up in the computations, right? Okay, Z alpha over 2. I'm looking at 95% confidence interval. I want half of 5%, so it's 0.025, 2.5%. I want Z 0.025, and you should know that's 1.96. You've done it enough times, I would imagine. So what is E? Margin of error is E 0.025 times the square root of P hat Q hat over N. That's 1.96 times 104 over 560. Is that readable? Barely. (104 over 560 times 456 over 560, all divided by n, which is 560, and that works out to be 0.0322 dot 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 dot. Okay, that's, if I'm going to round to the nearest hundredth, I should probably, looks like maybe round to 0.03, but you could argue, I am rounding down. I'm making my margin of error a little smaller, so I'm making my interval a little bit tighter. So I maybe am kind of fibbing when I say that I'm going to give you a 95% confidence interval. It might be a little bit less, right? If I shrink the interval for the same sample size and everything, I am decreasing my confidence. So like I was mentioning before. So maybe I should round up to 0.04. That's quite a bit of a jump to round up to 0.04. And so I'm probably going to have a much more than 95% confidence interval. But if I want to not lie, that maybe is what I should do. So maybe I have in my notes 0.03, but I think I would go to 0.04, rounding up. You know, I could go to 0.035 or something, and I wouldn't round up as much, but then I have 3 digits, and you might not want to go that far out, because if you round to the nearest hundredth, then it becomes the nearest whole number percent. And typically you don't want to give people like, well, 22.5% of voters, you want to just say 22 or 23 or whatever, right? So I'm going to round up to 0.04. And that's one that you might debate a little with folks, because you're really broadening it there. You might debate a little with your coworkers if you're working on this together. You're broadening it quite a bit there, but at least we're not fibbing and giving them a confidence interval that we don't really quite have by using the smaller one. All right, so what's the answer? The answer is a 95, really it's 95+% confidence interval is, I go, and again, we were off a little with our choice here by rounding to 0.19, so I guess it doesn't hurt. We're off-centered a little. It doesn't hurt then to make this bigger. So it's 0.9, let me just write it first in the compact way we have. It's 0.19 plus or minus 0.04, or it's what, 0.15 to 0.23, right? And I have, yeah, okay, that's good. So what is our final conclusion? I'm not going to write it. We are 95% confident. Write it in the context of this problem. Write it in the context of this problem. So the answer isn't just, we're 95% sure that P hat is between 0.15 and 0.23. Say what it is in terms of what we're actually trying to do in the problem. Okay. Okay, next page there. One more thing about confidence intervals for a population proportion. Consider our formula for the margin of error. E is Z alpha over 2 times the square root of P hat Q hat over N. Maybe it's time to try a different marker. We'll see. Okay, I say there that we can do a little algebra and solve this for N. We don't do much algebra in this class, but there's one place where we do a little algebra. I square both sides, and that gets rid of the square root, and I multiply both sides by n to get an n over here, divide both sides by e to get the e over here, but now everything's squared except the stuff that's under the square root. We end up getting the following. We get n is equal to z alpha over 2 squared times p hat q hat over e. All right? And you're saying, well, okay, yeah, you can do that, big deal. But this is very, very interesting. This is a very powerful formula, and I want you to see here why. It says that if I have every number on the right-hand side, I can find the number on the left-hand side. I can find the sample size that I need. If you tell me the confidence level, you're telling me essentially what alpha is. I can figure out what alpha is, which means I can figure out z alpha over 2, so I can figure out this number. If you tell me how wide you want your confidence interval to be, so you're telling me both confidence level and how big your interval is, you're giving me E for the size of the interval, right? Because wherever I'm at, I go up and down E, and there's my interval. So if you give me the confidence interval and the size you want your interval to be, I should be able to calculate the sample size. Except, I would need these values, wouldn't I? P hat and Q hat. And how do I get P hat and Q hat? I have to go through and take a sample and compute them all. So there's something circular going on here. I can't find n unless I have those, but I have to have, I can't compute those without n. So, you know, all along we've just had an n that we had. We had our sample size and we worked everything through. I would like now to be able to figure out what sample size I need before I start. Most of the time, if you go back and look at all the ways we have done confidence intervals, we can always solve for n, but the problem is it always depends on information that we would have to have already computed, already knowing n, right? And that's the same thing here, except for the fact that we can use calculus to show that p hat times q hat is always whatever the values are for p and q, which is 1 minus p hat and q hat, which is, q hat is 1 minus p hat. Whatever those values are is always less than or equal to 1/4, all right? And it is a little fact that you can use calculus to show that no matter how many successes I have or how few or how many, when I compute p hat times q hat, the number will always be less than or equal to 1/4. So in this setting, when I'm dealing with population proportion, this thing I can just replace with the number 1/4, and I know this won't be any bigger than that. So if I let my n be equal to all of this, where I put 1/4 in there, it will definitely be big enough if I let it equal this, equal what it is, this with the p and q in there, because p and q aren't going to be any bigger than 1/4. So n equal z alpha over 2 squared times 1/4 over e tells us the maximum, the max sample size needed to produce a confidence interval, to produce a, let me say it like this, a 100, 1 minus alpha % confidence interval with margin of error equal to whatever value you pick for E. So this is beautiful because it says that if I say to you, okay, I need you to go out and do this survey, and I want a 99% confidence interval, and I want you to give me that confidence interval so that it's within plus or minus 2%. Right, so I want a 99% confidence level, and I want a margin of error that's just 2%. You can figure out how big a sample you need to take to be sure that that will happen. And the formula is right here. Let me rewrite it over here. It's n equal z alpha over 2 squared times, and I can write it as 1 times 1 over 4e, right? I can put that 4 in the denominator like that. And so it's really z alpha over 2 squared divided by 4e. If you like that better. It's a little more compact. Z alpha over 2 squared divided by 4e. Okay, so let's do an example. And I'm ready for that, right? Yeah, okay, so I explain all that, and then what I say is, look, this is what we get, but the end you get here might not be a whole number. It might have a fractional part. Always round and up. All right, can you read that? This is getting kind of faded. Always round and up, because I need to give you an n that I know will work. If the n has a fractional part, if I go below that fractional part, I have a lower value of n than I know will work, so I always need to round up, even if that fractional part is small. Let's do an example. To compute a 95% confidence interval with the maximum margin of error of 3% for the proportion of voters who say they would vote for corrupt in the next presidential election, we need to get responses from a random sample of voters of size n equals, I'm not going to rewrite all that. I'm going to say it's, well, yeah, I'll rewrite my formula. It's z, okay, 95% is, I guess I did that down here, didn't I? It's 0.025. So I need to square that, divided by 4 times, you know what, I lost my square. Forgive me, folks, this is squared as well. If you do this algebra, you're squaring both sides, you're gonna have an e squared. I've lost my e squared. There should be a square there, right here. I didn't actually run through the algebra, I would have caught it, but you have an e squared. Okay, so yeah, so I'm getting this, and this is the example, right? This is the last thing in this lecture. And so what that becomes is it's a 1.96 squared divided by 4 times e is 0.03 squared. Is it not? 3% is 0.03. If you work that out, you get 1,067.1111 voters. They can't have a fractional voter. To make sure we have enough, we round up. So it's 1,068 people to answer. Voters answering the questionnaire. It might not mean that contacting that many is enough, because they might not all answer the questionnaire. Probably won't. So we need that many voters answering the survey. All right. So we need that many, and I say, yeah, that's the minimum number that we need. If we want to do better, the more we get, the more we can either shrink our interval or claim that we have greater confidence, right? All right, we will stop there.